That's fine.
You said that's your hat?
My pad.
Oh, pad.
Somebody seen get it.
Yeah, that's yeah.
So let's see a couple of announcements. So first of all, Sam wanted to. These mini schools happen twice a year. We always try to bring in some guest organizers. So I want to thank Davesh and Alexei Zinger, who are the guest organizers for this workshop. Also, if you could, for people who are coming non-locally, I gather people have picked up the reimbursement forms, but then we need to collect them. So if you could hand in your reimbursement form before lunch to Lynn outside, that would be very appreciated. And so the second talk this morning is by Davesh Maulik, who will give an introduction to Gromov-Witten invariants.
All right. Okay. Thanks. I was about to thank the organizers, but I guess that would be a little doesn't quite right work. So what I want to do in this talk. Well, all right. Let me say so. So this talk is going to be pitched at maybe somewhat different level than Jason's, in the sense that I want to give more of a, it's going to be maybe a little less precise, and I just want to give some kind of overview of, well, first of all, what do we mean when we talk about Gromov-Witten theory, but then also just some kind of overview of, kind of some early computations in the subject, and then also maybe try to say something about kind of more recent aspects. And we'll see how much I get through and how much I say, but the idea is that, I want to keep it somewhat informal, so just ask questions and things like that. So let me maybe begin by just saying kind of very vaguely what at least what I mean when we talk about the subject. So the setup is you want to kind of set up some kind of counting problem. So you want to count, maybe curves. Well, you start off with, let's say, a smooth projective variety. And what you'd like to do at the beginning is maybe you're interested in some kind of explicit enumerative question, which is you want to count curves of genus G. At the beginning, you maybe are interested in embedded curves of genus G, which lie in some specific homology class, living in some kind of homology class on your variety. So, curves of degree D of some genus on, on the plane, for instance. And well, to count them, you'd like there to be finitely many. So maybe you add some constraints, satisfying some constraints. For instance, you could ask them to kind of, pass through some number of points. Or maybe you want them to, have some tangency conditions. And so on. So that, if you actually write down some kind of parameter space of curves, and you add you draw these constraints. Here's some kind of mystery parameter space that Jason already defined that we'll talk about in a second. And then every constraint is some kind of locus. So this is constraint 1, constraint 2. And on an ideal world, they'd meet in finitely many points, and you just want to count what those points are. And in the cases of interest, when x is not all but the simplest varieties, setting up this kind of dream picture is actually pretty complicated. And there are many answers. That's somehow one of the interesting things of the subject. There are many ways you could try to model this problem. But the way that it's going to be relevant for this talk is to use what Jason already defined, these moduli spaces of stable maps. where when I think of a curve, I think of a curve really as an abstract curve. Rather than think of the curve as maybe sitting inside X, I think of the curve as maybe an abstract curve equipped with a map to X. And then the condition about the, for instance, what degree it lives in is a condition about the push forward of its fundamental class. Okay. And well, if I want to do some kind of intersection theory on a parameter space, I need to I want some kind of compact moduli problem. And so the solution that we work with is a space of stable maps, which the data here is going to be, for now, let's say C is going to be a nodal, for now connected, genus G curve. There's going to be a map from my curve to X with this property on the fundamental class. Okay. And then I add this stability condition, which just means that if I look at the automorphism group, if I look for automorphisms of my curve that commute with the map, I just want there to be finitely many. I want this group to be finite. Okay. And so the idea is that, well, okay, this is some kind of space. And it's one thing you can show is that it's proper. It has automorphism, so it has some kind of, I'm allowing automorphism, so the technical way to say it is some kind of a stack or whatever, but it doesn't really matter. It's something that, at least in principle, I can do some kind of intersection theory on. And for instance, now if I wanted to count curves, let's say I want to count curves C that pass through, that meet some cycles on X, for instance. So for instance, in a second I'll do the case where, let's say I have P2 and I have a bunch of points and I want to look for curves that pass through them all. Oops. Okay. Or pass through none of them in this case. Gosh. This is like, if I had my eyes closed, I think I would have done a better job. All right, let's try that again. Maybe I'll draw the curve first. There we go. There we go. Okay. Oh, yeah, sorry, that's P3. Yeah. All right, yeah, that's a good idea. Let's change it. Well, how could I try to encode that in a kind of moduli problem like this? Well, what I could do is I could look for curves with some mark points. Look for my parameter space could be a curve, and I guess I have 4 points on it: x2, x3, x4. And then I could write down a bunch of conditions. So I can write down some constraints. Well, the first constraint would be that f of x1 is p1, p1, p2, p3. F of x2 would be p2, and so on. Okay. And so this would be my parameter space. Every one of those points would give me some kind of locus here, and then I'm looking for the simultaneous intersection of them. Okay, something like that. So how would I try to set this problem up? Well, I can introduce some variant of this space where I'll have now some mark points on my domain. Okay. It's the same thing, except now I have a bunch of points on the smooth locus of my curve. And again, this kind of stability condition where I take into account these points as well. And so now how do I encode the condition that I want, like the first mark point to pass through some point on my target? Well, I have a bunch of evaluation maps that go from this moduli space to X. Where this map is just, the first one is just I see where the first mark point goes. So I just send a curve, a bunch of points on a map. I just send it to wherever it sends the first mark point, and so on for the other mark point. So for every mark point, I get a map from my moduli space to X. And at least geometrically, what is the locus where the first mark point maps to P1, the second mark point maps to P2? That's just going to be the intersection of all of these different loci. Now, if my moduli space were smooth, and proper, I could try to, count, assuming this locus was actually finite, I could try to count this using the intersection product on the cohomology of this moduli space. And what that would mean is, well, I could pull back the corresponding cohomology class on X, pull it back under this evaluation map, and then I could, multiply them together, cap it with the fundamental class of my moduli space. That would give me something that lives in degree 0, and then I could just take its degree. Okay. And this would be, well, this would be some kind of rational number. Rational because of these automorphisms that I've been kind of sweeping under the rug. Okay. And so this is how I would kind of set up this problem in the world of, homology and cohomology of my moduli space. And the idea is that, well, in an ideal world, this locus would actually have the correct dimension. They would all be meeting transversely, and the number of intersection points would then be computed by this kind of calculation in the cohomology ring of my moduli space. But of course, in the real world, none of these smoothness or transversality hypotheses are true. And so this is what kind of Jason was alluding to. So in the real world, we're not so lucky. And we have to use some substitute for the fundamental class. So in reality, these moduli spaces, well, they're proper, but otherwise they're terrible. Meaning in this generality, they're usually going to be reducible. They're not going to have components of the same dimension. And so even what you would mean by the fundamental class of such a space doesn't really make any sense. Usually you want the fundamental class to live in, cycle of, whatever the dimension is. But even the dimension of this moduli doesn't make any sense because different points will have different dimensions. Different components, will have different dimensions. But, and I'm going to sweep this under the rug for now, what Jason kind of, did a pretty good job of explaining, I think, is a substitute, which is that we think of this moduli space is cut out by some equations. And if we could deform these equations so that they were transverse, then that would give us something, some kind of cycle class that lived in an expected dimension. But even if we can't do that kind of deformation, we can still write down a class. So you write down a class. This virtual class that lives in some kind of expected dimension. Which in good cases, like in a second I'm going to do an example where you don't have to worry about all this stuff. Your space is actually going to be smooth and proper, and this will just be the usual fundamental class. But most of the time it's something more complicated that still has very nice formal properties. And so then what I mean, at least by the Gromov-Witten theory of X, just means intersection numbers of this kind. Well, I didn't have to ask for my curve to pass through some points. I can in general take some more general cohomology classes, maybe corresponding to some constraints. And instead of the fundamental class, I have this virtual fundamental class. But the idea is I should think of this as like counting the curves such that the first mark point maps to the cycle that's Poincare dual to this cohomology class. The second mark point maps to the cycle that's Poincare dual to the other second one, and so on. Okay. So these are really the simplest example. These are, for historical reasons, called the primary Gromov-Witten invariants, and you should just think of those as incidence conditions on the mark points of my curve. Okay. And I'm just going to use some notation. Gamma 1, gamma 2. Maybe G. Okay. Actually, in this talk, I'm really just going to stick with these. Okay. Are there any questions so far? I mean, this has all been kind of, Jason defined most of this already. But one thing I should say is, what is this expected dimension supposed to be? Because in order to get an actual number here, I want the number of constraints to kind of match the expected dimension. I need this to actually give me a number. And so what is this expected dimension? Well, suppose let's ignore the suppose I have a curve and a map. Let's ignore the mark points for a second. The way I would try to deform this curve and the map is, well, first I could try to deform the map. So deformations of my function, well, that's given by something like global sections of the pullback of the tangent bundle, because that's telling me if I have my curve mapping the first order, that's telling me how to deform, what direction to deform it. Okay. Well, there are also deformations of the curve, so that gives me an extra 3g minus 3. Now, this is going to be something kind of, not all of these tangent directions can be realized. There are going to be some obstructed directions, which come from some kind of H1. But now this is something very clean. This is some kind of Euler characteristic of a bundle on my curve, and this is just the deformations of the curve. And so if I do the calculation, okay, so this expected dimension ends up being, well, let's see, so something like, so beta is my curve class. This is the canonical bundle of my target, and I can take, I can pair one with the other. And I get this extra term. Now, if I had mark points, then those could just kind of move around on my curve, so that would add an extra n. Okay. And so the point is, this is the degree in which this virtual class lives. And the first thing to remember is that sometimes this will be the actual dimension. But it's very easy to write down examples where this is just completely wrong. So for instance, if beta equals 0, and I consider this moduli space, beta equals 0 means that my entire curve is getting contracted to a point. And so to tell you a point in this moduli space, I just have to tell you what point it's getting contracted to and what curve it is that I'm getting contracted. So this is just mg bar across x. Well, this is a beautiful smooth space, and its actual dimension is 3g minus 3 plus the dimension of x. But if you actually run through this calculation and see what you get something that is not equal to that. It's off by what you actually get for the expected dimension is 3g minus 3 plus the dimension of x minus g times the dimension of x. So you have to check your intuition a little bit. So in this case, for instance, the virtual class is not going to be the fundamental class of this smooth proper space. It's going to be something else. And I'll say what it is later. But the first example I want to do is a case where this really is going to be perfect. I mean, perfect meaning exactly what you would like. So the second thing I want to say is, so right now we have this moduli space, and because of these evaluation maps, you get lots of maps to x, and that's what I'm using to produce these kinds of these intersection numbers. But we have some more structure here, and that structure is kind of crucial for a lot of the nice properties. Which is I also have a forgetful map. Where I take a curve, a map, and a bunch of points on it. And I just forget f. Well, that gives me a curve and a bunch of points on it, and then I can, stabilize the curve. Meaning contracting any rational components that have positive dimensional automorphism group. And so this will give me a map from m, g, n, x beta to mg, n bar. Well, I guess I'll just call this pi. All right. So this is something where I forget the target completely and I just remember the curve. And this stabilization just means that, like, for instance, I could have a stable map that looks like this, where this component is non-contracted. But then this isn't the stable curve, so I need to contract that component. This would matter. Okay. And so there are two reasons why having this forgetful map is useful. One is that, well, it gives me, a richer collection of invariants, which show up kind of naturally. So there are two things I can do with this forgetful map. Well, one is, okay, so I have this forgetful map to mgn bar. One is I can kind of take interesting classes on the cohomology of mgn bar, so interesting classes on mgn bar. Like, for instance, I could take, there are all sorts of natural line bundles and vector bundles on mgn bar. I can take their Chern classes and pull them back. There's a boundary stratification on mgn bar. I can pull back those boundary classes. And I can pull them back and then throw them into the mix with these intersection numbers. So I can do this and then so this gives me a richer collection of invariants, which even if you care about these primary ones, these kinds of end up showing up along for the ride. Okay, that's one kind of reason this forgetful map is interesting. But the second has to do with this boundary stratification, which is that, well, if I pull back, well, first just set theoretically, if I pull back some kind of boundary divisor on MGN bar, this is built out of, simpler spaces of stable maps. For instance, suppose I had suppose I didn't have any mark points for a second. So let's say I'm just working with MG bar, and then I have a boundary divisor here where I just have a kind of curves with a single node, and the genus splits up into G1 and G2. Okay. So again, this is some codimension 1 in the moduli space of genus G curves. And so what does it mean to have a stable map that lives over this locus? Well, that means I have some kind of stable map of genus G1 mapping to X, and I have a stable map of genus 2 mapping to X, and each of them has a point, and they both have to agree at this point. So these 2 points have to map to the same point in X. So I could at least set theoretically, for instance, well, there has to be some degree distribution. But this locus I can write then as a fiber product of these simpler Oh, this is not a rational curve. Sorry, this is I was just circling the 2 points to indicate that.
Couldn't it be irrational?
Ah, yes, that's right. And so yes, but I mean, so these are. So, for instance,
Well, that's why it would be in the pre-image, but the 2 marked points wouldn't go to the same place.
Well,
Contracted to a point because it's.
if there are no mark points here, this would not be a stable map. Something like that.
So it would have to go non-trivially.
Ah, yes, but that could happen. So if this was, so then the idea is that. I'm not claiming that this is not a disjoint union, but the idea is that, for instance, the way I would realize this stable map, where this is is I could pick one of these nodes. This is my node, and then this is now a point here, and this is a point in this space, and then they both map to the same point over X. Sorry, these circles are maybe confusing, but.
No, John's question was this could be a stabilization of submaps. So there could be a chain of rational curves.
Oh, yeah.
Contracted, but it all has to be done mapped to a point. So this 2 marked point will still go to the same point in X.
Why do they have to be contracted in X?
I still don't think I understand the question.
Well,
Because
what Andre said was the question I was trying to...
which components gets contracted once you stabilize?
Yeah, all the rational curves.
Okay.
But I'm talking about in X.
Oh, okay.
They better not be contracted in X, or it wouldn't be stable in X. So you could have a chain of rational curves. They'd eat up some of the homology. The 2 points wouldn't go to the same place, so you wouldn't be in this sort
No,
of.
I'm not sure. I mean,
That
sorry.
answers your question. What? So I think you answered that question.
Right. I mean, so let's say this is a non-contracted curve.
Mhm.
This is my node. I mean, this point on this curve, this is a stable map to X of genus G1. This is a stable map to X of genus G2.
Is it point G1 X? Because you add that rational curve. Not changing G2.
But you could also describe it the other way.
Yes.
Right. Well, so this is just a union of these kinds of loci. But I'm not making any claims about it being a disjoint union. But now what's going to happen is that, for instance, well, there are going to be 2 ways of trying to understand, this locus. One is by intersecting my boundary divisor, by pulling back this boundary divisor and intersecting it with the virtual class on the ambient space. And the other is by taking virtual classes on these things and pushing them all forward and adding them up. And so part of the compatibility is that all of these things agree. So the idea is not only is the moduli space kind of, has this recursive boundary structure, this recursive structure is kind of compatible. This recursive structure is compatible with these, these virtual classes, which is what you would more or less expect in the kind of ideal picture, but it's true there. So this is kind of the first kind of key property of these moduli spaces and constructions. And the second one is, I guess, I don't know if Jason actually said it, is that these constructions are all deformation invariant in the sense that if I have, so that's maybe this is the first key property that we'll be using later on. And then the second key property, which in some sense is why we expect this theory to behave well, is that these Gromov-Witten invariants are all deformation invariant. Well, what do I mean by that? Well, if I have a smooth family of varieties, then the Gromov-Witten theory in any genus of one of the of any fiber is the same. Okay. I guess I should use B. Maybe I'll say it like this. Sorry. So Gromov-Witten theory of a fiber is independent. Even though these actual moduli spaces could be wildly different. So for instance, if I have a family of varieties, I'll have classes in H2 which could be represented by curves in one fiber but not in another. Put it another way, if I look at the space of one cycles on a variety, this behaves terribly in families. And in some sense, we're looking for the piece of information about these families that is somehow insensitive to those kinds of deformations of the complex structure. This is a very strong constraint, and in some sense, it's when we talk about, for instance, the Gromov-Witten theory of the quintic threefold, we don't have to we don't have to think too hard about which quintic threefold we mean as long as it's smooth. And so the fact that this, it means we get to ignore very subtle questions about existence of one cycles and focus, and then pass to more quantitative information. This can sometimes be a bad thing. For instance, you could be interested in counting curves on surfaces, algebraic surfaces, and the fact that they have, deformations where these curves vanish is maybe something you want to ignore. But for the most part, this is one reason why we have a hope of saying something quantitative. Okay. When did I start? Oh, okay. All right, I'm done with page 1. So let me do an example of a calculation in this subject. And this is really one of the first examples of something where you actually have a genuine enumerative problem, and you get to use this recursive structure to essentially crush it. But maybe before I do that, let me just say, so like I said, so the way I kind of think about this is that, a lot of the work in the subject, especially in the early days, was in the case when the domain curve is genus 0. And then we have kind of lots of techniques. And like I said, there's kind of 20 years worth of results. I mean, there's things of course, that are still very difficult about it, but there's been a lot of progress, I'd say. And then there's this kind of higher genus regime, where to be honest, frankly, there are very few techniques. But still, there's kind of conjecturally a lot of very tight structures. So, lots of kind of conjectural structure. And depending on your point of view, this is either kind of, depending on your, I guess, how optimistic you are, this is either a good thing or a bad thing. In some sense, there's something very frustrating about how little we can actually prove once we're in the higher genus regime. And then you can look at the story of rational curves to make you feel good about yourself. So okay, so on that note, let me do some examples of what things go well when we study rational curves. Like I said, so this is one of the basic examples, which is to count rational plane curves of degree d. So meaning, what I mean by this is really the most concrete thing you can imagine, which is that if I have a curve in P2 of degree d, so just, cut out by one equation, well, the arithmetic genus here, d minus 1 times d minus 2 over 2, and this is, the locus of such curves is some kind of, projective space, and then I'm interested in the ones where the geometric genus is 0. So for instance, I could impose, if I have delta, and whoops, if I have this many nodes, so then, and it's irreducible, then for instance, so that the normalization is actually at P1, well, the locus of, plane curves with this many nodes is some kind of locally closed stratum in my projective space of dimension 3D minus 1. And so if I really want to count them, I want to count rational plane curves that pass through some number of points. So I can count these curves that pass through 3D minus 1 generically chosen points. So there are lots of ways you could try to set this problem up. And the way this was done classically was to really think about the projective space of all plane curves of degree d and write down this stratum, which is the closure of the rational locus. And what you're asking for is you're asking to calculate its degree. So this is kind of one example of a severity degree. So the first examples of these are all pretty easy. So if I'm counting lines pass through 2 points on the plane, there's one of those. If I look for conics that pass through 5 points, there's one of those. Cubics, there are 12 of those. And then after that, it gets much harder. The next example that was worked out classically, again, using in terms of these severity strata, was for quartics, and that gives you 620, which was done by, is that Zoyton? And then actually the next number I didn't write down, so I don't remember what the next number is, and I also don't know who worked it out. But I figured Alexi might know. But I mean, well, I thought Ran had a proof. I thought Ran maybe did N5. All right. Okay. But it turns out one can work out the structure of these numbers very cleanly in this kind of stable map formalism. And this was done by Kontsevich in the early 90s. So phrase this by stable maps. And the way, just in terms of the language, in terms of the formalism that I said it before, is that you could try to look for a genus 0 Gromov-Witten invariant where the curve class is just d times a line and the homology of P2. And just in terms of that notation I was using before, what I do is I take 3D minus 1 mark points And I have an insertion for each one. So this is like this. P2, 0, D. Okay. Now one has to check, I mean, there's some kind of transversality statement that this is actually counting what you want it to count, and I'm just going to skip that. I mean, in this case, this space of maps is smooth. If I choose my points generically enough, all intersections can be made transverse. Okay. So really, this number will, in fact, be like completely genuinely enumerative. But let's just assume that for now and see how we can actually use this recursive structure to compute this. And the theorem that Konsevich showed was that these numbers satisfy recursion. Which is I'm just going to write it down. It doesn't really matter. I think that's right. Well, OK, so these numbers satisfy some kind of complicated recursion. And the point is that it's completely determined by this recursion. In fact, once you know that there is a line passing through 2 points, then the rest of the numbers in the sequence are completely follow. Right. Sorry. D2 is D1 minus D. So it's D2. D1 plus D2 is equal to D. So yeah, maybe I'll just write it here. So. Now maybe just because of time, and maybe I don't know how instructive it is. Maybe I won't do the detailed derivation, but I'll state kind of the principle of it, which is that the way this kind of contribution is going to show up is that I'm going to study the interaction between my moduli space and this boundary stratification. The idea so let me at least set up the argument. It's going to be so I'm going to look at the space of stable maps where I have 3D marked points. And what I'm going to do is I'm going to pick (3D minus 2) generically chosen points. And then 2 generically chosen lines. And I'm going to ask for the first 3D minus 2 mark points to map to each of these points. and then the last two marked points to map to these lines. Now, it's no condition to ask for a curve to intersect a line on the plane. So in fact, all the kind of dimension cutting is going to come from these point conditions. And so in fact, if I choose these generically, the locus this is going to be some kind of curve. I'm using the letter T for curve because I already used C, and I couldn't think of another letter for a curve inside of this moduli space. So now what I'm going to do is I'm going to take my moduli space, and I'm going to do one of these forgetful maps where I not only forget the map, but I'm also going to forget all but 4 of the points, and then stabilize. So I'm going to forget F, and then I'm going to forget everything between P3 and P3D minus 2. Whoops, X3, sorry. Okay. Well, M04 bar is just P1. And inside of P1, I have two, well, more than 2, I guess. But I can look at 2 different boundary strata. One is where x1 and x2 are on the same component. And the other is when they're on different components. Oops. 3D. Okay. Okay, these are 2 points here. And the point is, this is just points on P1. So these are linearly equivalent, or if you like, they're just the same cohomology class in the cohomology of P1. And so if I pull them back to my moduli space, the intersection number between T and this locus is going to be the same as the intersection number between T and this guy. So the kind of key fact is that because I have this very stupid linear equivalence on P1, if I take the fundamental class of T, let's see, what should I'll call this now? Forget. Where these are both times I'm looking at boundary strata, but with a different arrangement of points. Okay. Now what's happening when I take the preimage of this boundary strata? Well, there are lots of different, strata that can show up here because I've forgotten all the points and I have to distribute the degrees. So actually the preimage here is going to be a sum over all the different ways of distributing the degrees, and also a sum over all the way of distributing the points that I've forgotten about. And similarly for this locus. But the idea then is because, well, how do I construct an element of this locus? I'm going to have a stable map of degree D1, and I glue it together with the stable map of degree 2. And I do the same thing here. And if you just unravel what that means, one side, let's see which side gives which. So here, so the left-hand side of this equality gives me this equation. And the right-hand side of this equality gives me this equation. Now what makes this recursion work is that I never have degree D, I never have, the degree D contribution, n sub D, shows up on one side and not the other. And so let's at least see why that's true. But maybe the details of this calculation will omit. Right, so for this right-hand side, I have x1, and I have x3d minus 1, x2, and x3d. And so there's no way this curve could be of degree 0 because I'm imposing the condition that this point maps to P1 and this point maps to L1. And this point does not lie on this line. So therefore, there's no way this could be a contracted curve. And the same argument works here. So whatever the degree splitting is, this curve has degree d1, this curve has degree d2. Both of these have to be non-zero, which is what's happening on the right-hand side. I'm not allowing d1 or d2 to be 0. But on the left-hand side, well, these two have to map the line. So this curve could totally be contracted as long as it maps to the intersection point. So this curve could be contracted to L1 is equal to L2 as long as all the other marked points go to the left. The idea is this would have degree d. So the number that I'm interested in shows up on one side of the equality and not the other, and so the whole thing kind of goes forward. Okay. But I mean, what's going on here? They're really the key fact that I used. Well, one is this very stupid fact about this, linear equivalence of 2 points on P1, and the other is the fact that, the fact that the boundary strata, not only just as a locus, but also its fundamental class can be written as a sum of products of lower order fundamental classes. And the nice thing is, even if X were not P2, not a homogeneous space, you still get this kind of nice recursive structure as long as you work with these virtual classes. Okay. So let me now say, another way of formalizing what's going on in genus 0. Okay. Right. So yeah. So kind of the key facts again was this kind of stupid, equivalence of boundary strata. And then the fact that the fundamental class, and in general the virtual class, is compatible with the boundary stratification. And these facts are true for any X, and in fact, some version of this you can use in higher genus as well, but they always require some work to prove when you're not actually in the case where everything is smooth and projective. But now let me say something that you can do now for any target X, which is just kind of it's basically redoing the same trick now in kind of a slightly more formal way, which is define what's called the quantum cohomology ring. And so the idea, which is really cool, is we're going to define a ring deformation of just the usual cohomology ring of X. And we're going to use this genus 0 Gromov-Witten theory. So we're going to use, well, I'll just do what's called the small quantum ring. I'm going to use what are called the 3-point, so where I have 3 marked points, genus 0 Gromov-Witten invariants, to define the structure constants of my ring. Again, heuristically, if I think in terms of cycles, one way of thinking about the usual ring structure on cohomology is I have 3 cycles whose codimensions add up to the total dimension. And one way of phrasing the usual ring structure on cohomology is that I'm counting intersection points. Okay. This would tell me about, for instance, and the way of thinking about this quantum deformation is that maybe I don't care if my cycles intersect, but as long as I have a rational curve that meets all three of them, that will still contribute to the product where I weight this. By q to the degree of the curve. Ah, thanks. Well, so the way one often does it is you take the ring you work with is you look, for instance, oops. So one way of doing this formally is you can look at like the the monoid of effective curve classes in H2 and take the kind of algebra associated to that. If I had a polarization, then I could just evaluate that, and then I would just get power series. That's fine too. And the way of thinking about it is, let's say I just have, this is just my Poincare pairing. On cohomology, if I would take two classes and I wanted to find their quantum product, I can see what happens when let me just pair it with the third one. And the answer is going to be given by the corresponding three-pointed Gromov-Witten invariant. Okay. Well, this is just a definition. So the idea is that now this defines this, what gamma 1 times gamma 2 is. But the thing you have to check is that this actually defines a ring structure. In particular, the key fact is that this is actually associative. Well, and also, I guess what you call it, graded commutative too. I mean, it's graded commutative. And the unit class in cohomology is still a unit. It's still the multiplicative identity. Okay. And the key fact here is associativity, and the proof is just the same trick that I used for this Kontsevich recursion, which is that I take four-pointed stable maps, and I have this kind of forgetful map to M04 bar. And then I pull back the same linear equivalence that I used before. If I pull back this one, this tells me gamma 1 times gamma 2, then times gamma 3. If I pull back this one, this tells me about gamma 1 times gamma 3 and then times gamma 2. That's the same trick from before. And there are more general versions. This is called the small one for a reason, because there's also a big one. There's a more general version where it involves, not just three-pointed ones, but higher ones. And in those terms, like that, you can reprove that statement about plane curves very quickly. All right. But the key fact, is that what this defines is some very, nice deformation of the classical cohomology ring. And in good cases, we can just understand this completely. So for instance, a very easy calculation. I'll leave it. An exercise is just the case of projective space. Huh?
You have like 15 minutes.
Yeah. Okay. Is that okay? I mean, yeah. All right. That's right. I'm not. I mean, this more or less ends the stage of the talk where I say things that like we understand well, and then I'm going to talk about the higher genus case, where things are less clear. Okay. All right. So maybe I'll just do that now, actually. One thing I will say is that we have this ring structure, and there's more kind of algebraic structure that's encoded just by this forgetful map to M0 n bar. You can rephrase some of this in terms of a certain flat connection, and there's a whole bunch of structure there, and that all gets useful for just understanding how to calculate these invariants. So there's some kind of rich algebraic structure here that's used a lot. What happens in genus bigger than 0? Okay. Well, we still have this kind of these moduli spaces. They have lots of maps to X, these evaluation maps. We have these forgetful maps to MGN bar. And again, all these virtual classes end up being very, highly compatible with the boundary stratification and so on. And so you can encode, this data via, for instance, one way of thinking about this is that if I have a bunch of cohomology classes here, I can pull them back and push them forward. And I get a sequence of maps from the cohomology, tensor powers of the cohomology of X to the cohomology of MGN bar, satisfying a bunch of constraints coming from the boundary stratification and forgetful maps and so on. So this, if I axiomatize what kind of properties this satisfies, I get what's called a cohomological field theory. Okay. Which is going to be at least one of the things that YP is going to talk about, I think. Is that right? Yeah, okay, right, okay. So this is YP's talk. I mean, maybe one thing to say just about the higher genus, the aspects of the higher genus theory, is that we're very far now from, in general, we don't really have any expectation that this should, we expect the virtual aspects of these moduli spaces to be very prominent. And so kind of a very simple case is, let's say I consider, higher genus maps to P1 of some degree D. And so, for instance, the kind of object that you might think that's certainly contained here would be just a branched covering of P1. Okay. So some kind of, the kind of objects that would be encoded by Hurwitz numbers and so on. But in this moduli space, well, this kind of locus is very nice and has the expected dimension and so on. But there are also going to be stable maps where the entire genus G part is contracted, and then I have a bunch of tails maybe. And these count equally to the theory, and so you have to what happens is that these contracted curves end up heavily involving the cohomology of MG bar in some way. So like the simplest case is when I'm doing, again, I said degree 0. If I just do MG bar of X0, this virtual class here is not the fundamental class. It ends up being the top Chern class of a certain natural vector bundle on the space. Where this E is what's called the Hodge bundle. So this is the vector bundle whose fibers are just one forms on my curve. So this is some vector bundle of rank g times the dimension, which makes up for the difference between the actual dimension and the virtual dimension that I wrote before. And just in general, when you try to do these higher genus calculations, you immediately run into calculations about Chern classes of these kinds of bundles on the moduli space of curves, period. And there's some very rich interplay between these two subjects. Okay. But I will say, I mean, unlike the case of genus 0, where I give an example where this kind of, boundary stratification on the moduli space of curves almost completely solve your problem for you. That very rarely happens in higher genus case. So very rarely, sometimes, but usually, the higher genus story, is not, cannot be determined via the cohomology of mg bar. For most, I would say sometimes it happens, but very rarely. And so you could ask what tools that we have, but okay. Well, maybe okay. So I have 8 minutes left. So maybe instead of like I said, I mean, it actually won't take very long to say what kind of general tools we have. Oh. Right, yeah. Okay. So what kind of general tools do we have? We actually basically have very few. I mean, there's some progress that you can make using this kind of cohomological field theory stuff. But in general, I mean, the most useful tools we have are when, for instance, X has some kind of group action. And the smaller the fixed point locus, the better. And then you have some hope of using, for instance, a localization argument. To reduce whatever calculation you're interested in to something about the fixed locus. That works for toric varieties, for instance. It's not clean, but it's at least the start of something. The other general tool we have is kind of an extreme version of deformation invariance, where if I degenerate my variety to a union of two pieces, and then in this situation, we can understand how the Gromov-Witten theory of X is determined from the pieces. That again has some kind of problems, but at least it's something we can use. One thing we don't know how to do right now is if I degenerated to something with 3 pieces. That's already beyond our ability right now. So this is still kind of a very restrictive tool, but it's still. I don't think they can do the strong version of what I'm claiming. You mean you're talking about the log stuff? I'm talking about Brett. Oh, I see. Okay, this I don't know. Okay, sorry. Yeah. So I don't know what Brett is claiming.
He's claiming that he can do it.
Okay, all right, okay. So maybe this is now possible with 3 pieces instead of 2.
What's the shame of the answer?
Yeah.
Well, you have to ask him direct.
Yeah, okay.
Isn't those exploded vibrations?
Okay.
Okay.
Okay, so for the most part, these are really the most useful tools we have, or at least the ones that kind of work in the most generality. And any other case where we can prove something, it's really kind of, by hook or by crook. Sorry, I keep on losing the eraser. Oh, is it there? I see. So I have 5 minutes left. So, I mean, in the higher genus case, then let me just say a few directions. That are kind of interesting. So let me say one kind of direction, which is I view as kind of as an indication of how little we can do, which has to do with, for instance, so this is an example of an open question, which is, let's say I take the quintic threefold. So this is kind of the quintic threefold. Now in this case, the virtual dimension is 0, so for every degree you just get a number. For every degree in a genus, you just get some number. And in genus 0, now, I mean, I don't know, I guess 20 years ago now, we've understood how to calculate these. Okay, so this is work of Giventhal and Giventhal and Lu, Lian, Yao. Okay. And since then, I mean, so this is the predictions for these answers came from the physics literature by mere symmetry. And what that means concretely, from this point of view, is that there's some explicit answer in terms of hypergeometric functions. It's a little complicated to write down, but it's completely explicit. And if you look at the physics literature, there are answers for what these numbers are for higher genus as well. So in the physics literature, they can go up to genus 51, 52, 52? Okay. 50. Okay. 51 plus or minus 1. Okay. And again, I mean, the answer is kind of complicated, but it's explicit. And you can ask what we're capable of, rigorously. And well, okay, so Alexei Zinger can do the case of genus 1. This is, Zinger. And then that's it. So, I mean, the gap in terms of what's kind of, what answers we expect and what we can actually get our hands on is enormous. Okay.
Why did the physicists stop it?
Yeah, it's actually kind of an interesting. It's kind of an interesting. You could ask, what's so special about 51? And
they give you some space of functions in which this series lie.
Yeah.
That space of functions can be constrained to one dimension, to like zero dimensional if you're in low enough genus. Otherwise, still be predictions. Be saying some generating series belongs to some finite dimensional space of series.
Yeah. So the idea is that they have some generalized modular form. These numbers are coefficients of some generalized modular form, and then they have to figure out which one it is. And actually, the reason it's kind of funny. The bound that they have a bunch of ways of constraining it, and the bound that kind of screws them up is that at the end of the day they use the Castelnuovo bound for relating the genus of a curve and the degree of a curve, and that's like quadratic or square root depending on how you write it, and that screws them. So they get a bunch of linear constraints and they have this kind of square root constraint, and they all meet right around genus 51. Yeah. And actually, I mean, this has more or less been the status in the physics literature for a while. And like I said, I mean, obviously those guys are dummies and they can't do better than 51, but we can't even do better than 1. So, all right. So I mean, maybe so there are a lot. Okay. So in the afternoon we'll hear kind of more directions one can work on. One thing I can say, this is I think kind of a case where these general tools actually lead to a really good result, which is I'll just state this kind of the weakest version of this, which is that when the dimension of x is equal to 3. So these results are all along the lines where I do it genus at a time, where I take the genus and I look over all values of the degree and I see what kind of properties I have. So I'll state this maybe when x is Calabi-Yau, just to make my life easier. And here in the Calabi-Yau case, the virtual dimension is just 0. And so what I'm going to do is I'm going to fix the degree and sum over all values of the genus. Okay. Well, okay, so there's nothing here. And there's one subtlety, which is I'm going to do disconnected curves. Okay. And the claim is the conjecture is the weakest version of some kind of Schieffer conjecture is that this is a rational function in e to the I u. And this is just the weakest thing one can say. Conjecturally, we have kind of a very precise picture of what this generating function looks like. And the nice thing is about these general tools is that one can actually prove this. This is the theorem of Pandey and Pixton. Well, in this setting, one can actually prove this for, let's say, complete intersection Calabi-Yaus. So like the quintic threefold. And the proof uses these kinds of general tools, but it also involves, pulling, it also deeply involves understanding the relation with the moduli space of curves and so on. So, I mean, this is some kind of rich story, but this is at least a positive statement to go along with all these kind of negative ones where we're kind of stuck. All right, I will stop here.
Questions?
So in that case, do you expect that all cases, genus 2 or greater, are going to be handled at the same time, or does it actually get harder?
It depends on what you're trying to do. Yeah, I mean, the way people are doing it right now, I would say it's genus at a time. So for these questions, I want to fix the genus of sum over all values of the degree. And that seems to get harder. That seems to be a genus by genus process, which is the way people are thinking about it right now. There's some ideas for like more general techniques, but I mean, I don't know. I mean, what do you think, Melissa? I mean, the nice thing about this approach is that this is kind of a different question. I'm really fixing the degree and then studying all the genus at the same time. And somehow answers here don't seem to really help with answers here. I mean, there's kind of two different directions. Well, I mean, in the Calabi-Yau case, let's see. So I forgot he was. Huh? Basically equivalent. I mean,
Is it good?
Yeah.
Has been proved, right?
Well, I think, yeah, so okay, we can discuss this. I thought they proved some. Oh, I thought for every. I don't know if the statement they prove implies this, right? There's some.
Proved integrality. They have not proved the Castanova bound. That's what you.
Yeah, I mean, I thought they did. I thought there was some termination that they don't prove.
So they proved that these things are integral, but they have not proved that if the genus is high enough, then it's zero.
Yeah, right. So that's the statement I think you would also want here. Some vanishing statement.
So it's equivalent to both of them.
I can't remember. Yeah, I have to think about it. I don't want to say anything on tape. It would be held against me in a court of law.
St. Davesh again.